Tilburg University presents TAISIG Talks, the podcast that keeps you updated on the latest developments in the field of artificial intelligence in just 1 hour.
Welcome to the TAISIG Talks. My name is Pieter Spronck. I'm a professor of computer science at Tilburg University. Today I'm going to have a conversation with Afra, Alishahi and Hosein Mohebbi. And we will be talking about the interpretability of deep learning models of text and sound, which is a mouthful, but it will all become clear during our conversation. Afra, can you quickly introduce yourself, please?
Of course. My name is Afra Alishahi. I'm an associate professor at the Department of Cognitive Science and AI. And I am the leader of the research unit Computational Linguistics, which mainly focuses on building computational models for processing language data in various forms, in written and spoken modalities. And one of my research interests is to understand how these models actually work. So this is the topic that Hosein and I will talk about today, I assume. But the basic idea here is that since the state-of-the-art models are what is usually known as deep models, and these are very difficult to understand, we need special techniques and special methods for analyzing them and understanding what kind of information they process, how they make decisions, etc.
Okay. We'll get back to that.
Yeah.
Hosein.
First of all, thank you very much for having me. And I'm Hosein Mohebbi, a PhD student at Tilburg University at the same department as Afra, and I'm supervised with Afra, Grzegorz Hurpawa, Yelizav Dema, and recently Ivan Titov as well. And I'm working on interpretability of deep learning models for text and speech. And I'm also one of the co-organizers of Black Box NLP workshop, which is a workshop specifically for analyzing deep learning models for text.
So in general, this topic, interpretability of deep learning models of text and sound, I can imagine that lots of people know what the separate words mean, but how this comes together, they probably do not. So maybe we should unravel this. And let's talk about text and sound. So if we say text and sound, what do you actually mean? What kind of text and sounds?
So I think everybody has some idea of what machine learning and what data processing involves in general.
I wouldn't assume that everybody has an idea of that.
I assume people who listen to this podcast might have some idea. But the underlying principle is that you build a computational model that receives input data of some sort, right? And the sort of data basically defines the domain in which the model is being operationalized. Now, in the domain of language, which is typically called computational linguistics or natural language processing, depending on whom you ask, we usually work with two main modalities. We work with text, which is the written form of language data, and we work with speech, which is the spoken modality. Sometimes we add other modalities too. For example, we might pair text with image or speech with video frames or other kinds of combinations, but we are specifically interested in the linguistic characteristics of the input data. And so the science and methodologies built for processing with this particular type of data are very much informed by the characteristics of natural languages and their formal structure and their variation across different languages. And so when you build models for understanding these models, you should also keep in mind the linguistic principles and frameworks that are already developed over centuries by linguists, and also human behavior by computational psycholinguists and by experimental psycholinguists. So that's what separates computational linguistics and interpretability in this domain from other domains of machine learning, which also involve basically using very similar architectures, very similar principles, but processing different kinds of input data.
You want to add?
As Afra said, this is to me it's very interesting because maybe this is something that in the few years happened in specifically that we have one single architecture for that works for every type of inputs. Like it can be like some tokens or some words in the textual format, or can be some frames of input audios, or can be even some patches of the image. That we have a single model that a single architecture which is called transformer, and that which is the brain behind many models, many recent AI systems like ChatGPT and other novel models that works for all of this, and this is a good news in my opinion. So we can design some interpretability methods that customize for this type of architecture and try to have a deeper understanding of what is happening inside of these models.
Okay, so we talk about text and sound. Now, text and sound are different in the sense that text, you have words, and words are, you can, if a word is written, you know exactly what word it is. If a word is spoken, it might need some interpretation to know what exactly that word means. But what you now tell me is, and that's the next step, that is going to go into a model, to a transformer, and basically the same type of transformer could work with these separate words and with the sounds. Is that correct what I'm saying now?
The same architecture can be used for processing different types of modalities. The same architecture can be used for processing visual data, image data, language data in its written form or in its spoken form, but that doesn't mean that you can use the exact same model with the same configuration for both modalities. You have to customize this architecture for the domain that you're interested in, right? Especially because, as you said, speech and text have very, very different characteristics. They come from very different levels of granularity. Speech is a noisy signal, whereas text is a symbolic transcription of that signal, which disambiguates a lot of the, unclear aspects of it, but also is stripped of a lot of information signals that we already have in the speech that are lost when you transcribe them into text.
Yeah, so you mean like somebody types an answer in an email or on in the WhatsApp, and then you don't know what kind of emotion is behind the answer, and they start to interpret it wrongly.
Certainly, you lose emotions, you lose intonation, you lose emphasis, you lose a lot of information about the speaker, their age, their identity, their gender, their dialect. But at the same time, you also don't have to deal with the background noise. You don't need to guess which word was uttered when there is a car honking in the background. It's a much cleaner data to process, obviously.
Okay, so text and sound goes into this model. Model is trained with texts or trained with sounds, or maybe even with a combination. And you also mentioned that visual data could be involved there as well. But just training a model, I want to go to the next step, that just training a model is not enough. The model is going to do something. For instance, if you have ChatGPT, which is an application around such a model, that what that does is it generates text based on input text. So that's what the model is used for. So when you talk about the models that you work with, what do these models do? What are they used for? Is that pure for interpreting something, or is there actually, are these models meant for something else?
Basically, these models, basically the first version of Transformer that was trained in a very high scale on text was kind of doing some language modeling, mask language modeling task, that you have a input text and you mask some part of the text, some words, and then ask the model to predict them, to just fill in the text. And the same idea goes for also audios, where you have some audio which consists of some frames. But the thing is, as Afra said, you need to do a bit customization, because these frames are continuous. So you first discretize these frames of audio, and then everything would be the same as tokens in words in the text, because you again have some discretized input frames that you put into the model, and then ask the model to fill in some blanks that you mask.
Okay, yeah, but I find this a little bit confusing what you're saying now, because you have this model and you say, well, I can use this, for instance, to make predictions on things that I left out. Maybe, for instance, you have somebody speaking and then suddenly there's an interruption somewhere and some text is masked, is falling out, and you can try to refill that using such a model.
For example, suppose I'm saying that I'm a student in the Tilburg University, and then mask some part of the audio that I said, for example, and then you ask the model to fill out that part of the audio with the right representation, which is related to that part of the audio.
So is the use of the model separate from the model itself? So once you have the model trained, can you use it for, well, not anything, but for many different things?
So this is, I want to take a step back here,
Yeah, sure.
because we kind of jumped into transformers, but in fact, neural models of language and even deep models of language have a much longer history than transformers, but the principle behind them remains the same. The idea is that a lot of these architectures, including the original recurrent neural networks and then the later variations, were based on this phenomenon that we have observed in humans as well, which is when you hear an incoming utterance, you always predict what comes next. So this is a phenomenon that has been empirically studied both in children and adults. It's a very strong unconscious behavior where you expect things coming your way based on the context that you have received so far. And it's surprising how much can be learned about language based on just this simple task. So if you build a model, a very simple model that always tries to predict what is the next word if the model is listening to an incoming sentence, over time, if it reaches a point where it can predict the next words with satisfactory accuracy, the model has learned a lot about language. It seems like it's a simple task, but it's actually not only requires knowing a lot about the vocabulary of the language and also the syntax of the language, but also a lot about the semantics, the relations between different entities. So you basically this way build a whole lot of knowledge about linguistic structure and meaning into these internal representations of the model. And then you can use these representations for all sorts of different tasks. You can use them for language understanding. You can use them for generation. You can use them for mapping two different modalities together. For example, finding the best matched image for a caption, or building a description for an incoming image, all based on these underlying representations. Now, in more modern architectures, for example, transformer, you don't need to be limited to this sequential order. You don't only have to always predict the next word. You can actually cut a piece of the input and then have the model predict that, because the model is not exact. This architecture is not exactly sequential the same way that the recurrent architectures before were. And that's another dimension that makes these models better learners, in addition to a lot of other machinery and features that these models have. But the core idea remains the same, that the simple task of filling a gap requires a lot of knowledge about the language that they are exposed to.
And the thing that this model is trained on next token generation, which is even simpler than the previous test, that you mask some part of the input, right? And in this case, this makes much easier to use these models for any other tasks. So you don't have to train your model for every different domains. Like, for example, in the domain of text, you might want use your model for answering your questions, answering some factual knowledge or factual knowledge questions, or you might want use your model for sentiment analysis, just putting some part of the text and ask the model, this review, for example, is positive or negative, or use your model for paraphrase or summarization or everything. So the only thing that you need to just cast your input as a task of next token generation. For example, suppose I have a review, this is a great movie, I liked it, and then say, so this is mask. This is a mask, for example, movie, and then ask the model to replace, for example, the word mask if the model is trained by mass language modeling task, or if the model is trained based on next token generation, you can ask the model what is the sentiment of this review, and then the model, because it's trained on next token generation, tries to fill in the next that coming in the sentence. So in this way, you can solve your tasks.
Okay. Well, I have a lot of questions now. I don't know how deep we should go into all these questions, but it might be interesting to talk a little bit more about these models. Because you said, look, you can also do sentiment analysis. So I can imagine that you ask a text, if it's based on, or you ask a model, if it can predict mask words, so fill in a word here. And the word might be, I thought this was a movie. And it fills in good because before in the text occurred things like I like this, or I was impressed by. And that's because that combination, the word good fits there better than the word bad, exactly, because of the combination. But sentiment analysis is a bit more. This is a positive sentiment or a negative sentiment. If you look at data science, where this kind of sentiment analysis was done and still is done a lot, it's based on labeling things like this is a positive review and this is a negative review. So now I want to know what the sentiment is, but then there's an extra label involved there. So are you suggesting that you don't need that labeling anymore?
This is really depends on the engineer who sets things up. There are good reasons for doing it either way. So you traditionally you needed labeled data, and someone had to read pieces of text and say this is a positive review, this is a negative review, or use some indirect method, for example, using the ratings next to the textual review. And then you would represent these texts somehow by converting them to some, vector representation of some sort, and then you would train a classifier, which is its goal is to predict the ultimate label, right? You can still do that. If you have the labeled data, you can get the representations from these deep models. You can have the model process the text, they form some sort of an internal numerical representation of the text. You can take that text and then you can train a classifier on it, which is actually coincidentally one of the common ways of interpreting these large language models, which we haven't got to.
No, that's my next step.
But another, maybe by now people consider it a more organic way of doing it, is to if you have enough text data, I mean, how do we as humans actually go to Amazon and read product reviews and decide which one is positive, which one is negative? We were never given labels to decide, right? We read a piece of text, we decide this is a positive review or a negative review because we match these with our previous experiences, right? Mm-hmm. And so why not treating one of these models that are now able to generate text for us too with a prompt similar to what we do with humans? We would ask them, so what kind of movie was it? What did you think about the movie? So let's give the model a similar prompt and see how it describes the movie based on everything that it has heard before. So you're right, these are not the same kinds of approach, but they're pointing at the underlying learned knowledge about how text works or how language works.
Okay. Yeah, and we should make that step to interpretability, because we now know what the models of text and sound are and can do. At least we have an impression of that. And now you talk about the interpretability of these models. So what do you try to do with that interpretability? What does it mean, interpretability of such models? So now it gets really interesting.
Yes. So this is a very big question that how you can, give several different answers to them. But maybe the most intuitive way of talking about this domain, this newly, expanding domain, is to open the black box, right? So this is something that I think this is a metaphor that by now everybody is familiar with, that these modern deep models act like a black box because they're so complex that even though we know exactly what their mathematical core looks like, we really have a hard time understanding or predicting what comes out of them when we actually feed them with data. And that's where their power is, right? These are complex models. They can learn very complex patterns, but they are too good for us to fully understand them at the level of details. But that's not good, because these models are so powerful that we want to use them in several different domains, but these domains could have legal constraints for ethical reasons, for commercial reasons. We really want to know how these models process data, which part of the input data they pay attention to, how they make the decisions that they make. We want to ideally be able to explain them. And so there was always, from the very beginning when these neural models were developed, there was an interest in opening the black box, in analyzing them and trying to understand what's happening inside. People have proposed several different approaches. I mean, by now the number of techniques and methods is exploding by the minute, but the overall general approaches remain limited. The way people actually look at this problem from different points of view and by using different lenses. And many of these approaches actually do have their roots in the very early generations of neural networks. So you see some of these methods were used by people who actually proposed the architectures in the first place in the 90s. And by now they have become more sophisticated, but the ideas were there. Some of these approaches involve opening this black box and trying to manipulate the internal structure of the model. And this is something that is nowadays is much more common. And I think Hosein is perhaps the more qualified person to talk about them. But one of the earlier approaches was to actually treat them as a black box, the same way that we treat human beings. We want to understand, for example, how humans behave. We take them to an experimental room, we give them stimuli, we observe how they change their behavior. Why can't we do the same thing with models? We can, take them as an entity where we cannot open them up, but we can at least systematically control the input they receive and observe how their behavior changes and make inferences about the internal dynamics based on this change of behavior.
So yeah,
and I would add that the same thing goes also for our brain, right? This is a system that makes some decisions and do something, but we don't know what is happening inside. And many researchers are trying to understand this bit different kind of analysis with EEGs and other things. And the same goes for deep learning models, because they are also a kind of brain, but instead of, for example, synapse, here we have some weights that we model it as a metrics and some mathematics. And so the question is how these models works, and we are trying to open this black box.
Yep. So interpretability, I now get the impression is we want to know why the model is doing what it is doing. But that doesn't really tell me that much yet. So
I have to say this is one of the questions that you can ask, right? There are more questions to ask. So I can use an example from my research perspective, which is slightly different from the kind of question that you asked. So as I said at the beginning, or maybe I didn't, I don't know. One of my main research interests is studying human language learning, mainly in children. So for many years, I've been trying to build computational models that simulate this process of learning language. And in more recent years, with my collaborators, we've been looking at more naturalistic settings where you hear language in a visual context, and then you try to learn, what words mean, what the sound system of the language looks like, what you learn about the structure of the language, etc. And now we have these models, these architectures that seem to be doing this job very well at the, from an outsider's point of view. They seem to be acting very similar to humans while being trained on language data, right? Without any kind of knowledge being built in these models. They learn everything from the data that they receive, although, that's a controversial statement to make, but let's, for the sake of the argument, accept it. So a question that we were asking was, do these models really learn language or learn linguistic representations of the nature that linguists and psycholinguists have been telling us all these years? So do they learn a grammar? Do they learn, phonological categories? Do they learn one-to-many or many-to-one mappings between words and reference? How can you know the answer to these things, right? You see that the model does a certain thing, but you don't really know what kind of knowledge they've learned that has allowed them to do what they are doing. And so for us, for me, I'm now, I don't want to make claims for other people. For me, this was one of the most interesting questions, whether these internal representations have any parallel to linguistic theories that have been proposed over the centuries. But you can imagine that if you are building a deep learning-based system that is making very specific decisions, for example, receiving symptoms and then coming up with a diagnosis, or receiving applications and then deciding whether to grant a loan or not, what is interesting to you is based on what kind of evidence did the model reach the decision that it did, right? So the internal representations are not that much of a concern here. It's the dynamic of information processing that led to a particular prediction or a decision that is the most pressing issue in those domains. So people come to this interpretability domain from different points of view and with different needs.
Okay. And so if I understand it correctly, then you say one of the things you could do with this or are interested in is humans learn language. There are theories on how they do it. And we don't probably know for sure if these theories are all correct, but I know this has been studied for a long time, so I assume there's a lot of evidence that certain things work, and then you want to know, is this the same in these large language models? Because if it is the same, then you can probably make more predictions about how they work, how to maybe correct them, for instance, if they make mistakes, etc.
Yes.
And is that more or less correct?
Yes.
And is there another interpretation or another thing that you can do with this? That you can give, because I like this example, but there's much more that you can do, of course.
Yes.
Right. I can give another example, which is maybe we can call it localization of the knowledge in these pre-trained models, which is recently very popular in the interpretability community, which is called mechanistic interpretability, that you're looking for some specific circuits in your model, which is responsible for doing some specific task. For example, a good example that I always tell it to my colleagues is coming from David Ball's presentation in Black Box NLP workshop 2 years ago, that he showed that some specific neurons in vision models are responsible for modeling and understanding the concept of the light. And then if you just turn off those specific neurons in your model and then feed your image to the model with some light, then the output of the model turn off the lamp in that image, for example, or turn off any specific type of light, not just lamp, for example. And this is very obvious and can be interpreted for us because this is image, right? But in the context of text and speech, it might be more difficult to imagine. But again, for example, you can find some specific part of your model that is responsible for memorizing factual knowledge, let's say, or other kind of information that you can look for. And then if you can find these things, then you can edit the model. And this is the interesting part and the main goal of this process, because,
for example... Can I suggest another one in language? Maybe this, because I try to understand what exactly you're trying to say, but suppose I have a story, and that story there is a villain. Could I now, by, for instance, examining the model, find out where the concept of being a villain is stored, turn it off and turn the villain in the story into a hero in some way, so the story gets retold now, but it now becomes a heroic story? Is that what you think about? Or is this too far-fetched?
Yeah, maybe I need to...
maybe let me build upon that. Like your example is beautiful, but maybe it's a little bit too slippery, right, to pinpoint. But maybe in the domain of language, a famous example is gender biases, right?
Yes.
So famous examples from automatic machine translation systems where based on certain content words in the language, they always choose pronouns from a certain gender as opposed to another. And some of these biases lead to undesirable circumstances, right? So some of these stereotypes are actually harmful or incorrect, and people who develop these models want to prevent the model to make such generalizations, right? In such cases, but these models are, complex, and it's hard to know exactly how to control them. So it would be ideal if we could actually identify which part of this complex architecture is responsible for gender assignment, and then trying to control that portion, right, that circuit.
Yeah.
That would be a very, practical application of these.
But doesn't that assume then that would be in a very specific part of the model?
That's a very good question. So that's something that we actually can't be sure about, right? No. That you have a circuit or a part of the model that is customized and specialized for a particular kind of task. So the first step would be to build hypotheses about some of these tasks that are fundamental to the output of the model, and then try to look for them and see whether you find them or not. And a lot of the times you might not, because these models are known for distributing knowledge in a very distributed way. Representing knowledge in a distributed way. So it's not always the case that you have a specialized, sub model.
Yeah. So and actually this. I wrote a question down while we were talking about this, and that was if you understand the model, does it then mean that you can fix it in some way? Because, and of course, this is a very broad question, and the answer is probably in some cases yes, in other cases no. But the thing with these large language models is that they make mistakes. They make serious mistakes because there is no understanding, at least as far as I think about understanding involved in these models. They just have semantic links, etc. And but if you can dive into them and can pinpoint these kind of things, you could perhaps fix things so that they get more reliable. Although I think there's a lot of danger involved there. But maybe you can say something about this, because this seems to be a very interesting application of being able to interpret these kind of models.
Before answering this question, please let me clarify the thing that these new architectures that works now, that they are very good at capturing the context, the information in the context, and this is the main reason that these models do very well and better than previous architectures. So. This is very good because, for example, in this most easier way to exemplify this, suppose, for example, we want to vectorize our textual input, but we want to vectorize them based on the context. For example, the meaning of the word bank is really depends on the context, right? You can use it in the economical example, but it can be also used as some part of area next to the river, right? So you want to encode and vectorize those words, the meaning of those words based on the context. So at the same time, this is also a question, how much these models use the context and how much they can memorize some information and then use it and just store it in their weights, in the model weights, and then use it at prediction step when they want to make some decisions. So the reason that I mentioned the example of factual knowledge, because the factual knowledge are something that they are kind of unique. So for example, if you ask the model, for example, in which club Cristiano Ronaldo does play football, for example, the model might say that. For example, Real Madrid, because the most majority of data that the model was trained on was, for example, coming from 2 years ago, and then now you want to edit this specific knowledge, but the thing you don't want to train all of your model from scratch just because of editing some specific knowledge, right? It's a very difficult task and it's very expensive. So that can be an application of interpretability, just to try to find those specific circuits in your model that are responsible for memorizing factual knowledge, and then edit those specific parts without losing other information that is encoded in the model.
Okay, maybe because it's a fairly simple example, but And unfortunately, I don't know very little about football. So, but suppose you have a model.
Changed his club,
but you have a model that is trained on lots of information. From 2 years ago, all these players were at certain clubs. Then the player switches clubs, and you think, okay, what I can do now, rather than retrain the model, is just retrain this little bit of information in the model, so that the player is now linked to another club. The problem that I then think would happen is that probably by making a little change in the model, you're now also changing lots of other football players, and they're suddenly in different clubs. Because I cannot imagine that there's one link somewhere that links this player to that club. It's probably interwoven with lots of other things as well.
Well, that's another goal of these interpretability techniques, to see what the flow of information is and which parts actually affect other parts. It is, I think, the first times that some of these patterns emerged, it was surprising to researchers to see that it's not always the case that changing one part of the model affects other parts, mainly because these are so huge. And a lot of these information can actually be represented in a much more condensed way. So you could prune a lot of massive parts of the architecture without really affecting the performance of the model. So it's not like we really rely on every single node and every single connection in order for the model to act perfectly. So when you map these information flow graphs, you might actually notice that there are closed graphs. There are certain areas that are independent of other areas or have high influence on other parts, and changing a knob actually affects everything else. But this is not always the case, and that's the whole point of doing this analysis, to figure out these dependencies and try to come up with systematic ways to actually change things without breaking down the whole system.
Okay, can I? Because I try to know why we are doing this. Because that is a big question. So why would you work on interpretability of deep learning models of text and sound? Is try to make them better? Is that try to make them more? Is that the ultimate goal?
Not necessarily. No, I actually raised this question in some tutorial I was giving a few months ago. I asked people why they want to know how things work, and I received like 5 or 6 different answers, which were all valid on their own. It really depends on where you come from. You might be, simply curious.
Yeah, sure.
You are curious, from a scientific point of view, right? Yep. So a lot of these questions might be interesting from a learnability point of view. You want to know how a certain pattern is learnable from a certain type of data. Because these models are now doing stuff that previous generations of models simply couldn't do. So you want to know why, and you want to know how. But of course, they have also applied, like applications. They have applied purposes. Some of these purposes are simply uncovering and being able to explain how certain things happen. Some of these applications down the road would be how to intervene, how to adjust, for the reasons that Hosein explained, because these models are very expensive to train, right? And so you want to try to fix rather than retrain and hope for the best, because you never know if you retrain everything on a new data set, things turn out the way you want them to.
May I add one more thing?
Go ahead,
I'm
please.
just going to borrow Afra's point that she mentioned about the pruning of the model because they are huge. And this can be also another application of interpretability to make your model more efficient. And this, there is a very actually a hot topic in the research that they are very active to make these models. For example, let's say our model have some layers, and this is why we call it deep models, because there are many layers, and at each of these layers, model have some understanding and have some prediction. as much as we go further in the layers, this kind of information is mixed together more, and the model changes her decision, and something like that. So at some point, you might want to decide, for example, maybe for this specific type of examples, it's enough to just process just a few layers of your model, and then you can exit and not just process all of those layers. So this is an example of that you can exit quickly from the model and decrease the time of inference, the time of the time that your model is processing your input.
Yeah, I was actually at a conference last week where we discussed, and I didn't realize that was a topic, but I've done this topic. It's the small language models rather than the large ones, because the small ones you could run on a laptop or on a phone, and the large ones, of course, you need the internet for.
Yeah, and so there is, I mean, this topic is not very new, but it's still quite valid. The idea of distilling the knowledge in a language model, in a large language model, into a smaller version of it. By trying to get rid of all these, redundancies and
maybe also remove certain topics from it, etc. So,
but even if you don't want to lose any information, you could still, in many cases, you could distill a very large language model into a more condensed version if you do it properly without losing a lot of information. Actually,
very interesting. Okay, so I think the domain is now more or less clear, what the purpose is, etc., or what the purpose could be and what it does. But what is the state of the art at the moment? Could you say something about that? So where are we now? What would be the next steps that we need to undertake? How do we advance this kind of research?
That's a very good and tricky question.
Probably. Future you cannot predict, of course.
This is not going to end well for us researchers in the interpretability area. So a lot has happened. I mean, that's for sure. We have a lot of techniques, but you have to keep in mind that even though I said the history of these interpretability aims goes way back to the early 90s, this field really was resurrected and started moving forward in full force since about 7-8 years ago. Before that, there wasn't really much coherent effort into developing techniques, but suddenly it really exploded. So it started as some, workshops organized next to main conferences, and now this topic has a main track in every single computational linguistics conference, and it is one of the most popular tracks. Actually, it receives a huge number of submissions every year, and as a result of this rapid development, we also have a lot of inconsistencies in the efforts that people put into understanding the models. So let's say for a particular kind of purpose, there are suddenly 10 methods that people have suggested. And these methods are supposed to tell us how this target model works, right? In some way or another, right? Some aspect of it. What if these 10 methods actually tell us different things, right? Which happens all the time. I mean, that's one of the main issues in this domain, that there are major inconsistencies between different techniques for so-called describing or explaining what this model does. But if two methods give you two different, sometimes contradictory explanations, which one do you believe? So that's the downside of working in a field where there are no gold answers, right? There is no labeled data, and then you say, okay, my model has an accuracy of 72%, and your model has an accuracy of 65%. Therefore, my model is better. There is really very little gold truth in this domain. Of course, people have tried to come up with ways of evaluating these techniques that are reliable based on very strong hypotheses in controlled cases where we know certain assumptions must be true, but these are not very easily expandable and generalizable to every single case. So that's the main challenge that we are facing. On the other hand, we do have much more sophisticated methods for looking at different parts of these models, but also looking at different levels of granularity, as I said, not just saying, okay, if I remove this piece of input, this happens in the output of the model, but also looking at, okay, where certain types of knowledge emerge, in which layers in the model, in which components, but also focusing, like zooming into a single piece of input and looking at how this is Hosein's actually area of expertise, how you build these contextualized representations, which pieces of context you pay more attention to at which part of the information processing step. So a lot is happening, but we still are far from settling on things that everybody
otherwise
agrees
there probably wouldn't be that many tracks on a, a conference.
Probably.
But it's Afra refers to you, Hosein. So, what are you doing? Where do you see the biggest chances?
The disagreement problem that was mentioned was one of the biggest criticism that was always commonly voiced in the community, that why different explanation methods, attribution methods are disagreeing with each other. And attribution models are, we can think of some methods that telling us which part of your input is more responsible for the specific model prediction. And then at the first place that when transformers came out and they showed a very great performance, researchers have tried to adapt those methods for those general purpose interpretive methods that existed before for interpreting previous architectures to understand transformers. But they found that they had a very disagreement. They disagree each other, and then a lot of findings came out to see why this is happening. For example, the most simple attribution method that you can think of is remove and then predict. Yeah. You have a text. For example, in the case of sentiment analysis, you have a sentence. I like that was a great movie. Again, the same example. That was a great movie. I liked that. And then you pass it to your model, and the model says this is a positive review. And then you want to see which word is most important for the model to make this specific decision. So you remove the word, for example, great, and then you fit it to the model again, and then you can see the model output probability doesn't drop, although you expected to see that the model lose his confidence because you removed the most important positive cue in the context, right? And then when they looked at the internals of the model, if you remember, I said that this new architecture is very sensitive to the context, to the input. So this is the good thing that we really want. So when you remove the word great, there is another cue in the context that you said, I liked it. The movie was great. I liked it, right? So the model shifts its attention towards from the great towards the word like, the other positive cue. And this is why the model can fix it, and use the all positive context to make its a specific decision. So after that, a lot of other interpretive methods was proposed to fix this, to just to be based on mathematics of these models, to be customized for these models, and they show those methods was much more faithful than other general purpose methods in terms of reflecting the model's decision.
Okay, I can imagine that even if you say, well, you shift from the word great, well, the attention shifts from the word great because that is now removed to the word like, that you would also be able to make such predictions simply based on the length of sentences or the length of the whole review, or maybe even from the person who wrote the review.
Yeah, or even mixtures or combinations of these cues in the input, right? That's one of the main limitations of these so-called, input perturbation or input manipulation techniques, that you focus on one token at a time, whereas these models actually are good at capturing nonlinear patterns, and they might actually pay attention to combinations of cues or to cues that are not obvious to us. So this is maybe a good addition to what Hosein said, that when evaluating these interpretability techniques, people used to traditionally rely on what is nowadays called plausibility. So if a model generated an explanation that sounded plausible to us, meaning matching our heuristics, then the people found it more convincing. But that in reality, there is no reason for these models to actually rely on plausible cues. They might actually pay attention to cues that we never pay attention to and still make the correct decision at the end. So in that sense, there has been a shift from plausibility to faithfulness. We want to find explanations that actually are faithful to the decision-making process in the model.
Okay. So maybe something that I would like to bring up at the end is something that often comes up with AI research is that people start suddenly worry about ethics and things like that, and privacy, etc. And I can imagine that in this whole interpretability research that there is also things that come up there, because if you can change, for instance, models, or you try to look how you can change models, so then actually sometimes the reason is I want to make models in the end more ethical, but you might make them more unethical actually. So is there something that you can say about this?
Perhaps there is a whole domain, a legal domain. It's a can of worms. I'm not an expert. Maybe Hosein knows more. So feel free to add to what I'm saying. But at a very high level, there are two kind of conflicting points of view there when it comes to the ethics of interpretability and explainability. One is that you see certain behavior in the model that you conceive as harmful, and you want to contain it. The gender bias, the racial bias, the, giving all the loans to white men instead of, black women. These are the kinds of behavior that whoever wants to employ these models deems as undesirable. So you want to understand why these things happen, whether these things happen, how they happen, how we can actually control it. In these scenarios, you have your ethics decided in advance, right? You consider certain kind of behavior problematic. You want to make sure that your model doesn't behave that way. On the other hand, if you actually analyze your model and then you try to intervene for various reasons, right? For making it more efficient, for, fact-checking and editing and all that, which are practical decisions, right? And you come up with a solution that does what you want efficiently. It might, as you said yourself, it might actually have consequences for other predictions that this model makes in the future, which we didn't think about testing. And if these changes are not really grounded in data, in a way, you are claiming that you have trained your model on a particular data that you could check and you could control, but due to these interventions, you're actually making the model go beyond this original training data, and doing things that are not necessarily what they were supposed to be. Depending on the domain, this might actually lead to some behavior that some people might consider unethical.
Yeah.
Certain ways, right?
Yeah, because as soon as you start changing things, then you cannot claim anymore that it was objective, because you made decisions, and then the results of those, even if you didn't foresee them, might actually, you can no longer say, but it was the data. Yeah. Anything you want to add here?
Another example might be privacy, which is also kind of important in this case, because this model has trained on a lot of data, and if the data is, the part of data is private, then especially in this moment that these models are very human-like, interactive, you can interact with the model and just ask the model, for example, what is for example, Peter's phone number, and if the model was trained on, this can be also another kind of application of interpretability, to try to measure the information flow in the model and to just cut out those flow that is responsible for example, following information which is private.
Actually, this was a very good example, and another example that just to illuminate these non-trivial consequences. You might actually go to length to try to anonymize your data, right? So you might have, for example, therapy sessions between doctors and patients, and you might actually remove the identities of the patients from this data set, but someone manages to build a beautiful model that can analyze the internal representations and decode the gender of the patient, the age of the patient, the region they were born in, enough information that someone who has the right incentives can actually identify this patient. So these techniques that can tell us a lot about the internal representations of knowledge in the model can, if they fall into the wrong hands, they might actually reveal things that we don't want them to.
Well, I'm glad that at least these problems are considered. Is there anything that you want to add to all of this?
I would like to, because I know that the audience that will hear us might be interested in interpretability. That there is a interpretability tutorial was recently, just 2 weeks ago, was presented in the NACL conference by some people from Alishahi Institute and some US-based and Canada-based university. And they might be interested in checking those.
And how do they find this?
The tutorial title is Interpretability in the Era of Large Language Models, to understand what kind of techniques
in the era of large language models.
What kind of techniques we have for understanding these large language models.
Well,
this is together with the interpretability tutorial that we gave in the EASL conference, but that was for a specific interpreting specifically transformers. So the title of that tutorial is Transformer Specific Interpretability.
Okay. Well, thank you. People can look it up if they're interested in more. Well, thank you very much for being here.
Thank you for inviting us.
And I hope to see everyone in the next TAISIG Talk.